Alright, I'm making this video mainly for my 215 class and mainly to address the issue of what can go wrong in a proof using mathematical induction. So I want to take an example from the latest homework, which was the following. Prove that the sum of the first n odd numbers is equal to n squared. So 1 plus 3 plus 5, the first three odd numbers, gives you 9, which is 3 squared. So this is a statement we can prove in general for all n bigger than or equal to 1. And we want to do this using mathematical induction. Okay, mathematical induction, remember, needs three things. One, we need a proposition, and we need to show that this proposition is true for some base case, say p of 1. And we also need to show that if p of n is true, then p of n plus 1 is true. Given those two things, then we can state by the principle of mathematical induction, therefore p of n for all n bigger than or equal to 1. But we need to do those three things. First, we need a proposition that we show is true in a base case. Then we show this implication is true if p of n is true, p of n plus 1. And then we say, therefore, by the principle of mathematical induction, p of n is true for all n within our range, bigger than or equal to 1 in this case. How does that work in this case? First, we need a proposition. Let p of n be the proposition (1 plus 3 plus 2n minus 1 equals n squared). That is a proposition. It's a declarative statement which is either true or false. Let me show you what is not a proposition. That is not a proposition. That's an equation, one side of an equation. It's a summation. It's not a proposition. It's not making a declaration that's either true or false. This is just saying the sum of these odd numbers. If we say this is equal to n squared, that's a declaration. It's a proposition now. So to begin your proof, you need to start with some proposition. So let's start with, this is our proposition. P of n states this. Well, so let's take care of the base case first, okay? Prove p of 1 is true. Well, to do that, let's say what p of 1 says. P of 1 says 1 is equal to 1 squared. And we know that that's true. So p of 1 is true. Alright, that takes care of this step. We've shown that this is the case. I'm going to get rid of that. We need to show that given p of n, we can get p of n plus 1. So suppose p of n is true. That's the beginning of our proof. We're not saying this is true. We're saying suppose this is true, and we're going to show, therefore, p of n plus 1 is true. So we're supposing that this is true. What does p of n say? It says exactly the following. That's all p of n says. So if we're supposing p of n is true, we can write this is equal to this. Absolutely, it's exactly the same statement that we're assuming. We can then do whatever we want to both sides and still have an equality. So in this case, the trick is going to be to do the following. Add 2n plus 1 to both sides. So we've added this and we've added this to both sides of this original equality. We know from algebra if we add the same thing to both sides of an equality, we still have an equality. So this is absolutely true given this, which came from assuming p of n is true. Well, this right-hand side, n squared plus 2n plus 1 is n plus 1 squared. The reason for that, that's just algebra. We know n plus 1 squared equals n squared plus 2n plus 1. And so we've shown that the sum of the first n plus 1 odd integers is n plus 1 squared. So this is P of n plus 1. This is what P of n plus 1 says, and we've just shown that this is true. This is equal to this. Therefore, assuming P of n leads to P of n plus 1. That's this step. Therefore, P of n for all n bigger than or equal to 1. And that's by mathematical induction. So that's a good, valid proof of this proposition for all n bigger than or equal to 1 using mathematical induction. Alright, let me show you some of the things that can look like this but are not the same thing. So these are not what you want to do. So let me clear out some of this. And I'm going to put this in red. And I'm going to say don't do this. Alright, P of n says 1 plus 3 plus 2n minus 1 equals n squared. P of n plus 1 says 1 plus 3 plus 2n minus 1 plus 2n plus 1 equals n plus 1 squared. As soon as I do this, yes, I've stated what P of n plus 1 says. I've assumed P of n is true. I've made no assumption about P of n plus 1. So while this is what P of n plus 1 says, I have no way of saying whether or not this equality is true. And if I start working from here, everything that comes after is suspect. So for example, I can take this right side and I can say this is equal to n squared plus 2n plus 1. And then I can take this 2n plus 1 and this 2n plus 1 and cancel. And I can say that this is equal to n squared because of P of n. And so I've gotten n squared equals n squared QED. But that is not a proof of our original target theorem. What we did was we supposed that P of n was true. We also supposed P of n plus 1 was true. And from that we were able to prove n squared equals n squared. And that's all we've done. We've shown that P of n and P of n plus 1 proves n squared equals n squared. Well, if the problem had said prove n squared equals n squared, that's a good proof. But that's not what we were asked to prove. We were asked to prove, assuming this, that this is true, in order to prove that in all cases, n bigger than or equal to 1, this is true. And we haven't done that. We've shown n squared equals n squared. Now if we can start from n squared equals n squared, which we know is true, and prove that this equality holds, that's a good proof of this equality, which is P of n plus 1. But starting with P of n plus 1 and proving something that we know is true doesn't prove this. And let me give you the silly example of what this can lead to. So prove 3 is equal to 4. Well, I can say 3 equals 4, and I can say 3 plus x equals 4 plus x, and I can say y times 3 plus x equals y times 4 plus x, and then I can say let y equal 0, and this now becomes 0 equals 0, which we know is true. Therefore, I've proven that 3 equals 4. And that's clearly not a proof that 3 equals 4. All I've shown is that if 3 equals 4, then 0 equals 0. I have not shown that because this is true, this is true. And I better not be able to do that because we know this isn't true. In the language of propositional calculus, prove some proposition P, and down here is some proposition Q, and what we've shown is that if P is true, then Q is true, and we know that Q is true, and therefore we conclude that P is true. And that's a fallacy. That's the fallacy of affirming the conclusion. If you are a dog, you like bacon. You like bacon, therefore you are a dog. It does not follow. The only way to prove this, if you're trying to prove P, is to do something like prove that Q implies P and show that Q is true. Then we can conclude P. That's a good proof. If Q then P, and given Q we know P, that will work. But this does not prove P. It's a good old fallacy. So if you're doing this, it's really important that you only start with assuming P of n is true, and you work forward from that point, and you don't write down P of n plus 1 and try to prove something from that, because we don't know if P of n plus 1 is true. So the direction is absolutely critical. And I see pieces of the good solution in the homeworks. I see this step from here to n squared plus 2n plus 1 and turning that into n plus 1 squared. That means you're finding the insight. But to put it into a formal proof, you've got to be working logically. You've got to make sure each step follows from the previous step using one of the rules of logic. Indirect reasoning, modus tollens, something. And we're not seeing that if you start with something that we don't already know is true. Alright, that's just a quick overview of what can go wrong in mathematical induction, and for this example, what the correct way is to go about showing that. Alright, thanks.